Try another one. And right now, we're just using a table to evaluate these limits. So let's evaluate the limit as x approaches 0. Sine of x over 3x using a table. And again, we're going to use the calculator to help us out here, but yeah, we're just going to do a table here. And do need to look at it both sides, okay? And I separated into two tables. You can do it all as one, but be sure to look at both sides of the x approaching 0. All right, so what values, let's go on the low side of x is 0. What values over here, I'm going to approach 0, so what values would approach 0 here on the low side of 0, below 0? Well, it has to be a negative, and I do 0 because it's kind of different than your 2 and 3. What's the low one you want to try here? Getting close to 0, how about negative 0.1? Negative 0.1. Because if I did 0.9, that's closer to negative 1, isn't it? So, yeah. On the low side of 0, you go with negative 0.1. And like I said, I'm going to just do these on the calculator because it'll whip it right out. Just have to change my function. Do sine of x, parentheses, sine of x. And one other note on the trig functions, be sure mode, go to mode on your calculator and make sure you're in radians, right, for trig functions. Okay, mine is. So back to y equals, all right, so we do sine of x divided by 3x. Divide, not times, okay. And then go to the table here. And we're going to do negative 0.1, first of all, so that gives me a 0.33278. All right, what would be the next in line? If I want to get closer to 0 on the low side, I'm thinking on the number line here. Here's 0, so here's negative 1. So I did negative 0.1. So what's next? How about a negative 0.01? Yeah, to get closer to 0. In closer there, let's do negative 0.01, 0.3333. And then negative 0.001, even closer. It looks like we're locked in. The other thing I'd mention is, on the TI-84s anyway, if you go over to the Y1 part, it'll actually show you more decimal than it displays. This one is 0.333. There's actually 6 threes and then a 27778. The one above it is 4 threes and then a 2777. All right. So anyway, that's that. But I do need to look at both sides. So what would be on the high side? If I want to look at 0 approaching 0 on the high side, if you will, 0.1. Yeah. 0.1, 0.01. It does the same thing, just in the positive side. So 0 is the only one that does. You know, on most of them it's 0.9, 0.99, 0.999, then 0.1, 0.0. But on 0, it's the 0.1s on both sides. Okay, so if I do positive 0.1, positive 0.01, and positive 0.001, guess what? In this case, I get the same values as I did over there. All right, so it's 0.33278, 0.3333. And this is what, note please on the homework, this is what I'd like for you to display. I mean, you can figure out these limits and not show me a thing of work, but this is what I'd like for you to show. Be sure to show your tables on that. So anyway, what do you see? What is the limit then? So what would you say the limit as x, based on this little bit of work here we've done, what is the limit as x approaches 0 what are these values getting closer and closer to? Well, it looks like 0.3 repeating, right, which is 1/3. Yep. The limit there is 1/3. Okay? So that's how we're going to do this limit business. Right now, we'll look at different ways, of course. Just getting the idea down. Okay? All right. Let's talk about another limit as x approaches 0. This one, though, is we've got an absolute value. And it's absolute value of x divided by x. Let's notice a little something about this one. Okay, so again, we're approaching 0, so it's table-wise. I'm going to do basically the same thing that I had done over there, both sides. So I'm going to look at negative 0.1, negative 0.01, negative 0.001, and we could do more, but I don't think we'll even need to. And then on this side, we're going to do positive counterparts. See what we get. Okay, so plug that in to calculator. So we got absolute value of, which is under math on the TI-84s, math num, ABS. Absolute value of x divided by x. Table. All right, well, I've already got the 0.1s in here. The 0.1 is 1, the 0.01 is 1, and the 0.001 is 1. Okay? There's not much variation there at all. What about the negative 0.1 and so forth? Somebody got it? What do you get for the negative counterparts over there? What is it? What is the function value? This, of course, is the function. It's -1, isn't it? All right, so for one thing, they're approaching, as a matter of fact, they're equal to what on this side? They're -1, yeah. These values are going to -1. However, on the other side of things, they're going not to -1. They're going to +1. Well, what do we do about that? Well, you know, the other two examples, they were going to the same thing. So that was an easy, an easy answer. Well, the answer here is this doesn't have a limit as x approaches 0. Because for a limit to exist, it has to do the same thing on both sides. If it's going to 0.3333 on this side, then it better be going to 0.33 on this side for this limit to be 1/3. It's got to do the same thing on both sides. That's why I was stressing we got to look at both sides. Because if those values don't go to the same thing on both sides, like this one, the limit doesn't exist. This limit, the limit as x approaches 0, absolute value of x over x, does not exist. Why? Because the limit's different on one side than the other. All right. Now, this is a good time to mention here what we can do with this. Yeah, this overall limit doesn't exist. However, we can say we have some one-sided limits. There are some one-sided limits here. Okay. What we refer to these sides, the below side is usually referred to as the left side. So this is as x approaches 0 from the left, and then for obvious reasons we would say this is as x approaches 0 from the right. So what we can say is that the limit of this function does exist from the left. It has a value, and from the right it has a value. It's just that the two don't match. So we can break it up into one-sided limits and then give give values there. Here's the way we do that. If we're talking about the limit from the left, here's the way we write that. Like I said, that's the below side of whatever x value you're talking about. It's written this way. You put a little minus superscript on your 0. And that indicates that you're approaching 0 from the left, or the below of 0. Below 0. And let's just go ahead and... So that limit does exist. It equals -1. The limit from the right, guess what we do to indicate that? Well, we do the limit as x approaches 0 from the right with a plus. So the limit of that absolute value of x over x, it equals +1. Okay? We could have done that on all the others. We could have done the limit from the left and the right there, but you know, if they're equal, it really we really don't even have to write it down, because we can actually say what the limit is. But if they don't match up, we can break them into separate ones. Okay. Any question, concern on that? All right. I guess one other way we could say it then is go ahead and mention this right here. So another way we can explain the limit as x approaches a, f of x equals L. Another way we can state that is this limit equals L if and only if, I don't know if you've ever seen that phrase right there, but that's a pretty strong phrase. It means this goes both ways. The limit x approaches a of equals L if and only if, that was the IFF is the abbreviation for that, if and only if the limit as x approaches a from the left of f of x equals L and the limit x approaches a from the right of f of x equals L. Isn't that another way we can state what we've been doing? We're looking at the table from the left, the table from the right. So the only way this can equal L is if these two match. They equal both L2. That's what we're saying. Okay. All right, now, we've been looking at the table version here. Let's look at this from the perspective of the graph. Let's start with this one. Let's notice something here about the graph here. Did anybody graph that one? Or look at the graph. We've got it in there. That's another reason to do it right now. I've already got it in my calculator. All right. What does the graph of f of x look like? Well, if you look at the graph, it's just two horizontal lines, isn't it? And you think about it, that makes sense. But the graph of f looks like this. Here's -1. Here's +1. The graph comes in like this. Of course, it's not defined at 0, so it's open there. And then on the other side, that's open there because it's not defined at 0. It's undefined. But it goes out like that, you see. So another way we can think about the limit is by looking at the graph. And this one, it's clear it doesn't have a limit because the limit from the left doesn't match the limit from the right, does it? As you come in on this graph, you're coming in at two different levels. So that's another way we can verify or think about this limit. Yeah, so this is another way to see that the limit as you approach 0 of this absolute value of x over x thing doesn't exist. And D and E. You can use that acronym if you want to, for it does not exist. Okay. This is another way to verify it, because for the limit to exist, these two graphs have to come in at the same place. This one would have to come in here, and this one would have to come in at the same level, same place. Okay? Graphs don't match at 0. Okay? Let's go back to the f of x equals x minus 2 over x squared minus 4 graph. Graph that. We had that earlier. I erased it though, so let me put it back in. All right, so remember your parentheses, x minus 2 divided by parentheses x squared minus 4. Okay, so we got some kind of funny business out here, but that's we're looking at. We were looking at the limit as x approaches 2, wasn't it? We were looking at x. So this out here doesn't matter to us. So as x approaches 2, here's the thing: 1, 2, 3, 4. It looks like that graph just keeps on rolling through there, but actually we saw that at x equals 2, can the function actually exist there, or does the function exist there? No. So there's actually a hole right there. That's what's happening. The calculator doesn't exactly show you that, but at x equals 2, there is a hole there. But what we can see here is what's happening, even though the function doesn't exist at 2, this function, the graph, is coming into this point right here, and then it's coming into this point right here, and both of them are coming in at the same place, aren't they? That's why, and it's 0.25. That's another way we verify that, yeah, the graph, as x approaches 2, both of them are coming in at this level here. Now, one of them's coming from above, one of them's coming from below, so to speak. But both of them are coming into that one function value, the y value of 0.25. Okay? And so, just verifying there that the limit is 0.25. With me? Is that okay? All right, so to help, again, with this graph stuff, I've got 2 of them on here. We'll talk about the second one, hopefully in a minute. Pass it down. Let's look at number 1 on the handout there. Let me try to draw this up here. So number 1 on the handout, we've got, well, it goes something like that, and it goes right. 1, 2, 3, 4. That's at 5. Okay. All right. So number 1. A. Don't know the function, so there's no table, no nothing other than this graph to work with. All right, so what is this? What would be the limit as x approaches 2 from the left? And this is function f. What would that limit be? That is the limit as x approaches 2, and that's from the left. 2 below. What would you say? Is there a limit? Does it exist? Some of these may have an answer if it does not exist. Does this one exist? Yes, it does. What is the value of this limit? Somebody tell me. Take a guess. 3. Yes, it's 3. Yeah, it is 3. As you approach, as you approach 2 from the left, so I'm approaching 2 from the left, I'm coming in x, y is here. What is the function value doing? Well, the function value is coming up right there, coming up to 3. Now, does the function value actually exist at 3? No, but that's no matter. The limit, you see, is 3, isn't it? The function value, the function is going value-wise to 3 as x approaches 2 from the left. All right, let's flip that around. What's the limit as x approaches 2 from the other side? Plus side, right, from the right. Well, as you approach 2 from the right, you're coming in this way, so you're coming in right here, aren't you? What is that? I think it's my paper doesn't have. I think it's just below 1, isn't it? Looks like it's below 1. Let's call it 0.9, 0.9. Is everybody okay with that? Okay. All right, so what would you say the limit x approaches 2 f of x is? Trick question, right? What's the limit as x approaches 2? Well, for the limit as x approaches 2 to exist, these two have to be the same, don't they? Are they the same? No, they're not. This limit does not exist. Is that okay? All right. Okay, well, let's do another one. D, limit as x approaches 5 f of x. Okay, this is another tricky one. The limit as x approaches 5 f of x. What would you say on that one? Anybody just want to guess? Anyone guess 2? 2 would be right. Yeah, the limit as x approaches 5 of this function is 2, and that's because as you approach 5 from either side, and this doesn't specify side, so you got to look both sides. As you approach 5 from the right and 5 from the left, we're coming in, the graph comes in like this. That's coming in, yeah, it's coming in right here at 2. Now, note, what would this be? Is that 2 also? No. What's f of 5? F of 5 is, yeah, 1. It's a little bit low here, but it's supposed to be 1. Yeah, the function value is 1, but for the limit, that doesn't, in this case, make a bit of difference. It's what happens for the limit as you approach 5. The actual value at 5, in that case, is of no matter. Now, I'll say more about this in a second there, but what would you have the limit as x approaches 0 f of x at? Mine's a little off here. Well, as x approaches 0, we're coming in right here, aren't we? So the function's coming in here, so I'm going in right there, aren't I? That looks to be about, what'd you say? 1.7? Sounds good to me. About 1.7. Okay? Now we might note there, g, f of 0 is also what? 1.7. So in that case, the two match. See what I'm saying? These, they didn't match, but in that case it does, and that we'll say, like I said, we'll say more about that later.